let's start with just talking about conservation of mechanical energy. Under what circumstances is mechanical energy initial equal to mechanical energy final? Chess. Say it. When? Yes, when can we use this equation? It's not always true, because we need to know when we can use it. Victoria, help her out. This is only true when there's no friction. So it's a great place to start, is with the conservation of mechanical energy equations. Unfortunately, the reality is that there are plenty of circumstances where you need to deal with friction. So now, we're going to learn how to work with friction and with mechanical energy at the same time. And the way we do that is using the equation work due to friction equals the change in mechanical energy. And that is a boxed equation. The work due to friction equals the change in mechanical energy. Work due to friction. Buckler, what's the equation for work due to friction? No, I'm sorry. That's the right-hand side of the equation. I'm looking for expanding out the work due to friction equation. So what's the equation for work, and then plug in friction for it? I'm sorry, F?
Friction. Or force.
Force times what?
Displacement D cosine theta.
So in this particular case, it would be the force of friction, because we're talking about the work done by friction. Delta is a mathematical symbol, and it stands for a mathematical equation. Ciccarelli, what does delta mean?
Change.
I agree, you say it changes, what does it mean as far as math is concerned? It's an equation.
Like
Delta x, delta t, it always means.
the difference.
Right, but that's it, right, the difference, it's an equation. Nate?
The final minus the initial.
It always means the final minus the initial. So this means mechanical energy final minus mechanical energy initial. So notice the boxed equation is what you're going to get on a quiz or final exam, but the truth of the matter is that actually works out to be the force of friction times the displacement times the cosine of theta equals mechanical energy final minus mechanical energy initial. All right. Let's talk about the force of friction, the cosine theta, and this angle. This angle theta is, remember, always the angle between the force and the displacement. Therefore, it's the angle between the direction of the force of friction and the direction of the displacement. Remind me again, what are the three things you remember about the direction of the force of friction? Chas?
It opposes movement.
Opposes motion.
It's parallel to the surface.
Parallel to the surface.
And independent of force applied.
And independent of the direction of the force applied. So, in considering the fact that the force of friction is always opposes motion, is always parallel to the surface, and always independent of the direction of the force applied, and the fact that the angle in the work due to force of friction equation is the angle between the force of friction and the displacement, who can tell me what the angle is in your work due to the force of friction equation? Matt?
180 degrees.
180 degrees. Notice, the force of friction is always opposite the direction of the displacement. Now, I am going to put a little asterisk next to that, because there are people in this class who are going to take my AP class. And please realize that this is not true in my AP class. There are some specific instances where the angle between the force of friction and the displacement is not 180 degrees, and I will be going through that in the AP class. You can look forward to that. But in this class, we don't really go through instances where the force of friction actually causes the object to move. One other thing having to do with the force of friction, if you look at this, if we, say, all right, well, fine. What if we use this equation when there is no friction? If there is no friction, then the work due to the force of friction is equal to 0. This means mechanical energy final minus mechanical energy initial is equal to 0. We can add mechanical energy initial to both sides. we get mechanical energy initial equals mechanical energy final. Bless you. So notice that the conservation of mechanical energy equation is actually in the equation for the work due to friction equals the change in mechanical energy. You can just derive it from the fact if you have no friction, which means I don't actually have to give you the conservation of mechanical energy equation. I will, but realize that I don't. I mean, it's right there, right? Mechanical energy is initial equals mechanical energy final if there's no friction. So notice, conservation of energy is just a special case of the work due to friction equals change in mechanical energy when you have no friction. Okay. Let's do done. Oh, one small thing to make sure you understand. The work due to friction equals the change in mechanical energy is an equation, and hopefully you've noticed this, that we can use, but we don't have to use this. We could solve it in another way. As we get farther into physics, you'll discover that there are more and more ways to solve particular problems. So there are instances where you could use the work due to friction equals a change in mechanical energy, or you could simply draw a free body diagram and sum of the forces, figure out the acceleration, and use UAM. I will, under certain circumstances, require that you use this equation. You guys have a tendency, just like everybody, to stick with what you know rather than learning new stuff, and I will force you to use this equation rather than simply summing the forces, figuring out the acceleration, and using UAM.